somewhere out there is a place where every atom of you could stop existing or simply become unreadable forever. Welcome back to 101 Sleepy Space Facts. Tonight, we drift toward one of the strangest places in the universe, a black hole. Picture the darkest room you have ever been in. Then take away the walls, the floor, the air. Take away the very idea of a room. What remains is not empty space in the way your bedroom is empty when the lights go out. It is a place where the rules that hold reality together begin to stretch, bend, and possibly break. We are going to spend the next several hours sitting quietly with one question. If you fell into a black hole, what would happen to everything that makes you you? Not your body alone, but the pattern of you, every arrangement of every atom, every memory encoded in the folds of a brain, every small detail that made you distinct from anyone else who ever lived. Would that pattern survive somewhere, hidden from view? Or would it simply end, erased from the universe as if it had never been written at all? This is not settled. Physics itself is divided. Some of the finest minds who ever studied gravity and quantum mechanics have arrived at answers that cannot both be true, and no one has found a way to make them agree. That disagreement sits at the heart of everything we will explore tonight. Let's begin with scale, because scale is where wonder starts. Imagine floating far above our galaxy, the Milky Way, looking down at its slow spiral of light somewhere near its center, hidden behind clouds of dust and starlight, sits a black hole with a mass equal to about 4 million suns. It is called Sagittarius A star. From this distance it looks like nothing at all, just a small dark patch where light seems to bend around an invisible weight, and yet everything within a certain distance of that patch, once crossed, cannot come back out. Not light, not radio waves, not you. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Now drift closer, past the outer stars of the galaxy, past the slow orbits of gas clouds that circle the center like moths around a lamp they cannot see. As you approach, nothing marks the danger. There is no glowing line, no warning sign, no wall of light. The edge of a black hole, called the event horizon, is invisible by definition. It is simply the distance from the center where gravity becomes strong enough that escape requires speed faster than light itself allows. Past that line, every path, every direction you could possibly travel leads only inward. If you crossed that edge, your body would feel nothing unusual in the first instant. No door would slam behind you. No sound would announce the crossing, because sound cannot travel where you are going. This is one of the quieter mysteries of a black hole. The edge that erases you from the outside universe forever might feel, from the inside, like nothing happened at all. But someone watching you from a safe distance would see something very different. To them, you would appear to slow down as you approach the horizon, your image stretching and dimming, your light taking longer and longer to reach them, until you seem to freeze there forever, fading like a photograph left in the sun. Two honest observers looking at the same event would describe two different stories. Neither would be wrong. This mismatch between what falls in and what is seen from outside is one of the threads we will follow all night. Some researchers wonder whether the information describing you, the exact quantum pattern of your atoms, gets smeared across that horizon like a shadow painted onto a wall as you pass through it. Others wonder whether that same information simply survives, tucked inside the black hole, waiting for a physics we have not yet discovered. The two ideas cannot both be complete answers, and for now, neither can be ruled out. For the rest of this night, we will move slowly through what is known, what is guessed, and what remains genuinely open. We will look at gravity, at time, at the strange radiation that might let black holes fade away over long stretches of cosmic time. We will not rush toward an answer, because there may not be one waiting for us yet. Let your eyes rest, let your breathing slow, and let your mind hang quietly at the edge of this question, the way starlight hangs at the edge of a horizon it can never fully cross. Let's start with something simple. A black hole is not a hole at all. It is a place where matter has been pulled so tightly together that gravity becomes stronger than anything else in the universe. Picture a star many times heavier than our sun. Now picture that star folding inward, smaller and smaller, until all of its mass sits inside a space no bigger than a city. That is the beginning of a black hole. The gravity does not stop growing once the star collapses. It keeps pulling forever on everything nearby. Here is the strange part. If you were falling toward one, you would not feel yourself falling. Gravity pulls on every part of your body at the same time, at the same rate, so nothing would tug at you from any single direction. Your coffee cup would float beside you, the same way it does right now, sitting still on your nightstand. Your heartbeat would feel normal. Your breathing would feel normal. You would look down and see nothing marking the edge, no line drawn in space to warn you that something has changed. This edge has a name. It is called the event horizon, and it means the last place where light can still escape and travel back out to the rest of the universe. Cross it, and even light curves back inward, forever. From the outside, this line looks solid, almost like the surface of a dark pond. From the inside, there is no line at all. There is only the space you have always known, still quiet, still ordinary, right up until it isn't. Some scientists describe this moment as no drama, a strange phrase for something so enormous. The idea is that physics, as we understand it, predicts a calm and uneventful crossing. You would not feel a war. You would not hear a sound. Your body, for a little while, would remain exactly your body, still made of the same atoms, still holding the same shape. But other researchers are not so sure the crossing stays calm. One competing idea, called the firewall hypothesis, suggests that the horizon might not be a smooth boundary at all. It suggests that something at the edge could turn into a wall of extremely high energy, one that would burn away anything crossing through in an instant. If this idea is correct, the fall would not feel gentle. It would end the moment it began. These two pictures, the quiet crossing and the sudden wall, cannot both be true. Physicists have not agreed on which one describes reality, and that disagreement sits at the center of one of the strangest debates in modern science. Think about what that means for a moment. Two different mathematical descriptions, both built on careful reasoning, both respected by serious scientists, point to two different endings for the exact same event. One says nothing happens at the edge. The other says everything happens at the edge. The universe does not seem to mind holding two answers open at once, at least for now. It is our understanding that has not caught up. If you did fall in, and if the calm picture turned out to be true, you would keep falling for a while, watching the darkness around you grow. There would be no sound, because sound needs air, and space near a black hole is nearly empty. There would be no light from behind you reaching your eyes, not for long, since even the light from your own body would struggle to escape once you passed the horizon. Your body would keep functioning, at least briefly, unaware that it had already crossed into a place with no way back. This is the part that makes black holes different from almost everything else we study in space. With a star, or a planet, or even a nebula, we can imagine standing close and looking at it. With a black hole, the horizon is a boundary that erases the very idea of looking back. Once you are inside, there is no photograph to take, no message to send home, no way to describe what you see to anyone outside. Whatever happens next happens in a place cut off from the rest of existence. None of this tells us yet what happens deeper in, closer to the center, where the true mystery waits. It only tells us that the beginning of the fall might be the gentlest, most uneventful part of the entire story. Whether that gentleness lasts, or whether it was never real to begin with, remains an open question that we will keep circling back to, slowly, the way a moth circles a distant light. Every black hole once had a different life. It began as something else entirely, something that shone. Picture a star many times larger than our sun. For millions of years, it burns quietly, holding its own weight up with heat from its core. Deep inside, hydrogen fuses into helium, and that fusion pushes outward, balancing the crushing pull of gravity. This balance is delicate. It cannot last forever. Slowly, the star runs low on fuel. It starts burning heavier elements, one after another, each one giving less energy than the last. This process speeds up near the end. A star might spend 1,000,000 years burning hydrogen, and only a single day burning silicon. Something that took ages to build can unravel in an afternoon. When the fuel finally runs out, there is nothing left to hold the outward push. Gravity, patient this whole time, wins. The core collapses inward, falling in on itself in less than a second. Matter, that once filled a space larger than Earth, gets crushed down, smaller and smaller, faster than sound can travel through it. What happens next depends on how much mass the star had to begin with. Some stars leave behind a dense ball called a neutron star, where a teaspoon of material would weigh as much as a mountain. But if the collapsing core is massive enough, roughly 3 times the mass of our sun or more, nothing known can stop the collapse. There is no pressure strong enough, no known force able to push back. The core keeps falling into itself, forever, as far as our current physics can tell. This is the moment a black hole is born. Not an object exactly, but a boundary, a place where enough mass has gathered into a small enough space that gravity has sealed off a piece of the universe from the rest of it. Some black holes may have formed a different way, in the earliest moments after the universe began. Dense pockets of matter, packed together before stars even existed, may have collapsed under their own weight. These are called primordial black holes, and their existence remains a hypothesis. We have never confirmed one directly. It is one possibility among several for explaining certain patterns we see in the sky, but the evidence is far from settled. There is also the question of the giants, the supermassive black holes that sit at the centers of galaxies, including our own. Some may have grown slowly, swallowing gas and merging with other black holes over billions of years. Others may have formed quickly in the dense, chaotic conditions of the early universe, skipping the slow build-up entirely. Astronomers have found black holes that seem too large and too early for the slow growth story to fully explain. Both ideas are still being tested. Neither has won yet. What all of these origins share is a kind of quiet violence, followed by a permanent quiet. The collapse itself takes almost no time at all, cosmically speaking, but what comes after can last forever, or something close to it. A boundary has been drawn in space, and once it exists, it does not really go away. It only grows if it feeds, or shrinks, if it slowly leaks away, over spans of time longer than the universe has yet lived. If you had stood near that dying star in its final moments, you would have felt nothing unusual for a long time. The star would have looked much as it always had, a steady point of light. Only in its last day would anything have visibly changed, and only in its final second would the true collapse have happened, hidden from any outside view until it was already finished. This is part of what makes black holes strange to think about before sleep. They are not built slowly, the way a mountain rises or a coastline forms. They arrive suddenly at the end of something else's long life, born from an ending rather than a beginning. And once the boundary closes, the details of how it formed become almost impossible to read from outside. A black hole made from a giant star and a black hole made from a slow merger of galaxies can end up looking, from the outside, nearly identical. That fact alone is part of the larger mystery this episode sits with. If a black hole's outside gives away so little about its past, what does that suggest about what it does to information falling in later? The birth of a black hole erases its own history behind it. Whether it erases yours too, or simply hides it somewhere we have not learned to look, is a question still open, still being turned over quietly in the dark. A black hole is not made of the things you might expect. There is no rock here, no metal, no frozen gas. There is only mass, spin, and charge, folded into a shape so tight that space itself gives way. Everything else, the iron, the water, the carbon in your own bones, falls in and stops being separate. It becomes part of one smooth curve in space and time. Think about where your body came from. The calcium in your teeth was cooked inside a star that lived and died long before the sun was born. The oxygen in your lungs came from a similar furnace, deep in a star's core, released when that star scattered itself across space. Every atom you carry has a history older than the Earth. A black hole takes all of that history and folds it into something with no visible parts at all. This is one of the strange truths about a black hole. From the outside, it has almost no features. Physicists often say it can be described with just 3 numbers: how much mass it holds, how fast it spins, and whether it carries any charge. That is called the no-hair theorem, and the name is a small joke. It means a black hole has no extra detail, no fingerprint, nothing that hints at what fell into it. A star made of hydrogen and a spacecraft made of steel would leave the same trace if they carried the same mass and spin. That idea is where the first quiet unease begins. If a black hole truly has no memory of what it swallowed, then something troubling follows. The specific arrangement of atoms that made up a star, a moon, or a person seems to vanish, leaving only a number behind. Physics does not like that. One of its deepest rules says information should never be destroyed, only rearranged. A black hole appears to erase it completely, and that gap between what should happen and what seems to happen is still not settled today. Here is where space begins to bend in a way you can almost picture. Near an ordinary star, gravity pulls gently and light moves in mostly straight lines. Near a black hole, the pull grows so strong that light itself starts to curve. Time slows as well. A clock placed near the edge would tick slower than a clock far away, and the closer it gets, the more dramatic that slowing becomes. This is not a trick of instruments. It is a real feature of space and time bending under enormous mass, first described by Einstein's theory of general relativity. If you could hover near that edge and look back at Earth, you would see time on Earth moving faster and faster, as if the whole planet were living out years in the time it takes you to blink. Your own heartbeat would feel normal to you. From far away, though, an observer would see you moving slower and slower, your motion stretching out longer than a human life could hold. Two true pictures, both correct, simply seen from different places in a curved space. Some physicists think about this bending as a kind of building material. Instead of atoms, a black hole is built from the geometry of space-time itself, pulled into a shape so severe it closes in on itself. Others focus on a different question: whether the surface of a black hole, the boundary called the event horizon, might act like a thin skin holding information about everything that ever crossed it. This is the seed of an idea called the holographic principle, which suggests that everything that falls in might be recorded on that boundary, like a shadow keeping a memory of the object that cast it. It is one idea among several, and no one has proven it describes what truly happens at the edge. The competing view is quieter and more unsettling. It holds that once something crosses the horizon, no boundary can hold on to it in any usable form. The information may be scrambled so completely that even a perfect calculation could never recover it. Both views agree on the mathematics far from the edge. They disagree sharply on what happens right at the border, in the space where our best theories of gravity and quantum mechanics no longer speak the same language. You do not need to solve this to feel its weight. Somewhere in that disagreement sits the answer to whether the version of you that fell in could, in principle, ever be reconstructed from the edges of that vanished shape. For now, the geometry keeps its secret, curling that question into itself, the same way it curls light, time, and every atom that has ever crossed inside. Picture yourself falling toward the black hole, feet first, calm and quiet. Your flashlight is still on. You click it toward the stars behind you, sending one last beam of light out into the universe you are leaving. That beam is a message. It carries a picture of this moment, the last moment anyone far away might ever piece together about you. What happens to that light and to you is where the real forces begin to show themselves. Light behaves in a strange way this close to a black hole. Gravity here is not just strong. It bends the very path that light takes, curving it the way a lens curves a beam of sunshine. Some of your light escapes outward, stretched and dimmed. Some of it bends back and falls in with you. A distant observer, watching through a telescope, would see your light arrive slower and slower, redder and redder, as if your last message were being delivered through thickening honey. You would feel none of this stretching. From where you sit, your flashlight still works exactly as it always has. This is the first force worth sitting with. Gravity does not act the same way for you as it does for someone watching from far away. Physicists call this time dilation, the slowing of time near a strong gravitational pull. It is not a trick of the eye. It is built into the fabric of space and time itself, confirmed by clocks on satellites and by light bent around distant stars. But even with that confirmed piece of physics, no one has directly observed what a human body would experience at this exact threshold, because no one has ever come back to describe it. The second force waiting for you is tidal force, the same gentle tug that pulls the ocean toward the moon, but here turned up to an extreme no ocean could survive. Near a small black hole, the pull on your feet would be dramatically stronger than the pull on your head, because your feet are simply closer to the center, That difference in pull is what stretches things. Around a stellar mass black hole, this stretching would begin long before you reach the horizon, the invisible boundary past which nothing returns. Some researchers call this dramatic stretching by a playful name, though the channel prefers to simply describe it. Your body would begin to elongate, slowly at first, the way dough stretches before it tears. But here is where the mystery opens rather than closes. Around a supermassive black hole, the kind found at the center of galaxies like our own, the math works differently. The horizon is so much larger and the pull so much gentler at that boundary that tidal forces might stay mild for a while. Some calculations suggest you could cross into a supermassive black hole and feel nothing unusual in that instant, the stretching arriving only later, deeper inside. If that is true, then the moment of crossing carries no local sting at all. Your body would report nothing wrong at the exact horizon, even as the outside universe already considers you gone. There is also a magnetic and radiative side to this story. Matter falling toward a black hole often does not fall alone or quietly. It joins swirling disks of gas, heated by friction to millions of degrees, twisted by magnetic fields into brilliant jets that shoot outward across thousands of light years. This glowing material is part of how astronomers have found black holes at all, since the black hole itself emits no light. If you fell in the middle of one of these active disks, radiation and magnetic turbulence would likely reach you long before gravity's stretching became the dominant force. A quieter black hole, one not actively feeding, might offer a gentler approach, at least for a while. None of these forces, gravity's bending, time slowing, tides stretching, radiation's heat, answer the deeper question this channel keeps returning to. They describe how you would be pulled apart, physically, mechanically. They do not tell us what happens to the information your body represents, the specific arrangement of atoms that made you who you were. Some physicists argue that arrangement gets smeared across the horizon like a photograph pressed flat. Others argue it slips through untouched, preserved in a form we cannot yet read. The forces themselves are measured and modeled with real confidence. What those forces do to meaning, to identity, to the pattern of a person remains open. For now, picture only the light. Your last beam sent outward, stretching redder, dimmer, slower, carrying its quiet, unanswered message toward home. Let's talk about time and how strangely it stretches near a black hole. Picture two clocks, one belongs to you, falling toward the black hole. The other belongs to a friend, watching from far away through a telescope. Your clock feels normal to you. It ticks the way it always has. Your heartbeat, your breathing, your thoughts, none of it feels slow at all. But your friend sees something very different. From far away, your friend watches your clock tick slower and slower as you get closer to the edge. Your motion begins to look sluggish, like a video buffering. The closer you get to the horizon, the boundary past which nothing returns, the more your friend's view of you seems to freeze. Your image would grow dim and reddish, stretching toward the edge in slow motion that never quite finishes. In their eyes you would seem to hang there forever, never fully arriving. This is not a trick of the eyes. It comes from how gravity bends time itself, an idea confirmed by more than a century of careful measurement. Strong gravity slows the passage of time, at least as seen from somewhere weaker, down on Earth. This effect is small enough to ignore in daily life. Those satellites orbiting our planet have to adjust for it constantly to keep their clocks correct. Near a black hole, the effect grows enormous. the distortion becomes the whole story. To feel the scale of this, try a comparison. Imagine the sun shrunk down to the size of a basketball. On that scale, Earth would be a peppercorn drifting about 26 yards away, and the nearest star beyond our sun would sit thousands of miles off. Space is mostly empty distance now. Shrink a black hole the same way a black hole with the mass of our sun on this same basketball scale would not be a basketball at all. It would collapse down to a marble smaller than a pea, just a few millimeters wide. All that mass, all that gravity, folded into almost nothing. That is the strange scale of a black hole. Enormous pull, packed into something impossibly small, and the closer you creep toward that marble-sized point, the more warped the surrounding space and time become, until the warping becomes total at the horizon itself. Here is where the mystery deepens. From your own perspective, falling in, nothing about this slowing is noticeable. Your clock never seems slow to you. You would cross the horizon in a finite, ordinary feeling stretch of time, perhaps seconds, perhaps longer, depending on the size of the black hole. You would not feel yourself freeze. You would not feel time stretch like taffy. To you, the fall would seem continuous and unremarkable, at least for a while. So which is real? Are you frozen at the edge forever, as your friend sees it, or do you fall through smoothly, as you experience it? Both descriptions come from the same equations, from Einstein's general theory of relativity, and both are considered valid within that theory. This is not a disagreement about facts. It is a disagreement about which viewpoint counts as the true story of what happened to you. Some physicists argue the outside view and the inside view must somehow both be correct at once, each complete on its own terms, an idea tied to something called black hole complementarity. Others wonder whether this apparent agreement papers over a deeper problem, one where the two views cannot actually be reconciled without abandoning some cherished rule of physics. If you were the one falling, this mismatch would not feel like a puzzle. It would feel like nothing at all, just the quiet continuation of your own existence, unaware that somewhere far behind you, your image was still crossing the edge in the eyes of someone watching. Your friend would spend the rest of their life, and long after, watching a version of you that never quite disappears, fading redder and dimmer, approaching the horizon without ever technically reaching it, at least not in any finite time they could measure. This is the scale that makes black holes so hard to hold in the mind. Something the size of a pea can bend a friendship's shared sense of time into two different stories. Something invisible, smaller than a marble, can stretch a single fall into an event with two irreconcilable endings, depending only on where you happen to be standing. The mass is small. The consequence is almost too large to picture. No one has watched a real person fall into a real black hole. Of course, everything here comes from theory, tested only through the mathematics and through indirect observations of the universe's most extreme objects. Whether time near a horizon truly splits into two equally valid stories, or whether one story is somehow more true than the other, remains an open question physicists are still turning over quietly, the way you might turn over a stone you already suspect has no bottom. Picture yourself floating just outside the event horizon. That is the invisible edge where gravity becomes so strong that light itself cannot climb back out. You would not see a wall, you would not see a surface the way you see the surface of a moon or a planet. There is no ground here, no texture to touch, no color to name. And yet something is there, something real enough to end every question you might ask about what lies beyond it. If you looked straight ahead, you might expect blackness, and in one sense, you would be right. But the black hole would not look like a flat circle of nothing. Light from stars behind it would bend around its gravity, smearing into a thin, glowing ring. This is called gravitational lensing, and it happens because gravity curves the path that light travels. The stars behind the black hole would seem to slide around its edge like reflections on a curved mirror, stretching, doubling, sliding past each other in slow, silent arcs. Closer in, near the horizon itself, something even stranger happens. Light that grazes the black hole at just the right angle can loop around it again and again before escaping. If you were floating there, you might see the back of your own head, endlessly repeated, dimmer each time, curling into the dark like a photograph reflected in two facing mirrors. This is sometimes called the photon sphere, a place where light can orbit the black hole in a perfect, trembling circle. No one has photographed this from the inside. It remains something we calculate, not something we have seen. The horizon itself is not a place you would feel yourself cross. There is no click, no wall, no signpost. Many physicists describe it simply as a point of no return, mathematically defined, invisible to anyone falling through it. Some researchers wonder whether something more dramatic happens there. An idea called the firewall paradox, which suggests the horizon might behave less like a smooth doorway and more like a wall of extreme heat, destroying anything that touches it instantly. Other physicists disagree, arguing that a falling observer should feel nothing unusual at all, at least not right away. The two ideas cannot both be fully true, and no one has found a way to test which one describes reality. If you could hover just outside this edge, time itself would look strange to you. Light climbing away from the horizon would stretch into longer, redder wavelengths, a phenomenon called gravitational redshift. Anything falling toward the black hole would appear to slow down the closer it got, frozen more and more against the dark, its light fading toward invisibility. From your position outside, you would never actually see it cross. You would only see it approach forever, dimmer and dimmer, like a lamp being carried into fog. This is one of the strangest parts of the mystery. From the outside, nothing ever seems to finish falling in. From the inside, by every calculation we have, the fall continues normally, and crossing the horizon happens quickly and quietly. Both descriptions come from the same equations. Both are considered valid depending on where you stand. Physicists have not resolved how to fully reconcile these two views into one single story of what happens to a falling body. If you were the one falling, your instruments might show nothing unusual as you crossed. No barrier, no flash, no signal that says, this is the edge. Only later, deeper in, would the pull of gravity begin to feel different between your head and your feet, a stretching we will explore soon. At the horizon itself, many models suggest there is only a boundary written in mathematics, not matter. It has no thickness, it has no known texture, it exists as a threshold, a place where escape becomes impossible, but perhaps nothing else changes right away. And that is what makes this surface so strange to imagine. It is a wall with no bricks, a door with no handle, no frame, nothing to touch. You cannot land on it, stand on it, or press your hand against it and feel resistance. It is defined only by what it prevents, the boundary past which light and information can no longer return to the wider universe. Whether that boundary quietly destroys you, gently absorbs you, or to something else we do not yet have language for, remains one of the open questions sitting at the heart of this mystery. For now, we can only picture it from a careful distance, watching the light bend, watching the ring glow, wondering what waits just past that trembling edge. Past the horizon, gravity does not stay gentle for long. Close to a black hole, gravity pulls harder on whatever is nearer to it, and weaker on whatever is farther away. This difference is called a tidal force, the same kind of pull that raises ocean tides on Earth. But here it grows to a scale that no ocean could survive. If you fell in feet first, your feet would feel a much stronger pull than your head. The distance between them is small, just the length of a body. But near a black hole, even that small distance is enough to matter. For a very large black hole, the kind found at the center of a galaxy, this stretching happens slowly. You might cross the horizon and feel almost nothing right away. Your body still whole, your thoughts still your own. But for a smaller black hole, one just a few times the mass of the Sun, the stretching begins with sudden and complete violence, long before you ever reach the horizon at all. Some researchers describe this difference simply as size deciding your fate. A gentle unraveling in one case, an instant one in another. The word scientists use for this stretching is spaghettification. It is a strange, almost playful word for something that is not playful at all. Picture a strand of pulled dough, thinning and lengthening under the hands that stretch it. That is what tidal gravity does to matter, pulling the near side harder than the far side, until the space between your head and your feet stretches like that dough, and everything in between goes with it. Atoms do not resist this kind of pull. The bonds that hold molecules together are strong, but tidal gravity near a small black hole becomes far stronger, and at some point the stretching wins. The mystery is what happens to the arrangement of those atoms once they are pulled apart. Every atom in your body is still there in some form. Physics does not destroy atoms, not even here, but the pattern they made, the exact structure that made you a person and not just a scattering of matter, that pattern may not survive the stretch. Some physicists wonder whether this pattern, this information about how everything was arranged, gets smeared thin like the stretched dough itself, spread so wide and thin that it becomes unreadable, though maybe not gone. This is where the deeper puzzle waits. If information about your exact structure is only smeared, only hidden by the stretching, then in principle it might still exist somewhere, encoded in the light and particles that eventually leave the black hole. But if it is truly destroyed, erased rather than just hidden, then something more troubling is happening. Physics has a rule, one of its oldest and most trusted, that says information is never fully lost, only rearranged. A black hole that truly erases it would be breaking a rule that has never been broken anywhere else in the universe we can observe. Your body, if you were the one falling, would not know any of this while it happened. There would be no sound, no final scream that anyone could hear, no light escaping to warn you. You would simply stretch and thin at the pace that the size of the black hole allows, while your own thoughts and sense of time might already be behaving in ways that no one outside could ever confirm. This is one of the strangest parts of the mystery. The person falling and the person watching from far away would never agree on what happened next, or when, or whether it happened at all in any moment they could share. Some theorists propose that quantum effects, the strange rules that govern the smallest particles, might change this picture entirely near the deepest point, softening or altering what classical gravity alone would predict. Others hold that Einstein's equations tested and confirmed in so many other settings, describe the stretching correctly all the way down, with no correction needed. Neither side has proof the other side would accept as final. The instruments needed to test the difference directly do not yet exist, and may not exist for a very long time. What stays constant in every version of this story is the fading of structure into something we cannot yet describe well. The atoms persist. The pattern that was you begins to lose its shape. Whether that pattern is destroyed, hidden, or simply spread too thin to read again is a question that sits at the edge of what physics can currently answer. Beneath the surface of every black hole, past the point where light can return, this quiet unraveling is still being studied, argument by argument, equation by equation, with no agreed ending in sight. Once you cross the horizon, the outside universe does not vanish all at once. It arrives in slow motion. Light from distant stars still reaches you, stretched and dimmed, and for a while the sky above you may look almost familiar. This is one of the strangest rhythms in this whole mystery. From your side, time moves forward in a normal, steady way. There is no bell that rings, no wall that appears. The horizon, that invisible edge past which nothing can return, offers no signal at all. But something is happening in the background, something slow and patient. Outside, at the horizon itself, physicists describe a faint glow called Hawking radiation, named for the physicist who first predicted it. This radiation is thought to leak away from the black hole a little at a time, carrying off tiny amounts of energy across enormous stretches of time. For a black hole with the mass of a star, this process is almost too slow to imagine, stretching across time spans longer than the current age of the universe many times over. It is less like a candle burning and more like a glacier, losing a single drop of water every few centuries. This slow leak is one kind of cycle. Matter falls in, and energy trickles back out, though not in the same form. What comes out is not you. It is not your atoms, your memories, or the specific pattern of your body. Hawking radiation appears to be nearly random, a kind of warm static with no return address. If you fell into the black hole holding a photograph, the radiation that eventually escapes carries no image of that photograph, at least not in any way we can currently detect. This is the heart of a puzzle physicists call the information paradox, and it remains genuinely unresolved. One idea holds that this radiation truly is featureless, and that whatever made you you is lost from the universe forever once you cross the horizon. This would be a strange kind of erasure, quiet and total, with no explosion and no drama, just a slow return of unremarkable energy, where a whole life used to be. If this is correct, then somewhere in the deep future, long after the black hole finishes evaporating, the last trace of you would already be gone, dissolved into radiation that remembers nothing. A competing idea suggests the opposite. Some researchers, working from a framework called the holographic principle, propose that all the information about everything that ever fell in is somehow smuggled out, hidden in subtle correlations within the radiation itself. Under this view, the pattern that was you never actually leaves the universe. It gets rewritten, scrambled almost beyond recognition, but not deleted. Recovering it would require reading correlations spread across the entire radiated output of the black hole, collected over a length of time, so long it strains ordinary comparison. No one has done this. It remains a mathematical possibility, not a completed measurement. This unresolved back and forth is itself a kind of rhythm, playing out across decades of theoretical work rather than across nights and days. Physicists propose a model, find a flaw, revise it, and propose again. The firewall idea, which we will look at more closely later, is one of the more recent turns in this back and forth cycle, suggesting the horizon itself might be a far more violent place than the calm, gentle crossing we have described so far. Other physicists push back, preferring the picture of a smooth, uneventful passage. Neither side has produced a full and settled answer. If you think of your own body as an arrangement, a specific and unrepeatable pattern of atoms, then this cycle asks a very personal question. Does that pattern end at the horizon, or does it travel outward again, disguised in a slow trickle of radiation, waiting across eons for someone or something to notice the pattern and read it back? The universe does not appear to answer quickly. Black hole evaporation, on the scale of a massive star, unfolds across a span of time so long that comparing it to a human lifetime barely makes sense at all. For now, you can hold both possibilities gently, without needing to choose between them. One says the story of you closes quietly at the edge. The other says the story continues, hidden, scrambled, still technically written into the universe somewhere. Both remain open. The cycle of falling in, radiating out, and slowly fading away continues in the dark, indifferent to which answer turns out to be true, and indifferent too to how strange it is for us to wonder about it at all. Picture your feet pointing down toward the black hole and your head pointing up away from it. This is not a strange position. It is simply how you would fall, the same way you fall in a dream, arms loose, body relaxed, but your feet are closer to the black hole than your head, and that small difference, just a few feet of distance, is where the trouble quietly begins. Gravity does not pull evenly on an object. It pulls harder on whatever is closer to its source. Near Earth, this difference is too small to notice. Your feet and your head feel almost the same tug. But near a black hole, especially a small one, that difference grows and grows the closer you get. Your feet feel a much stronger pull than your head. Your body starts to stretch, gently at first, like warm taffy being drawn out on both ends. Scientists call this effect tidal force, the same force that raises ocean tides on Earth when the moon pulls harder on the near side of the planet than the far side. On Earth, the difference moves water a few feet. Near a small black hole, the same kind of difference could pull a human body apart. Some researchers use a blunter name for this outcome. They call it spaghettification, a stretching so complete that a body becomes a long, thin thread of matter, still falling, still lit faintly by whatever light remains. If you fell toward a small black hole, this stretching would happen fast and would hurt, at least for the short time your nerves still work. Your body is not built to survive being pulled apart at the level of its own cells. But size changes everything here, and this is where the mystery gets quietly more interesting. Near a very large black hole, one with a mass millions or billions of times greater than our Sun, the tidal force at the event horizon, the boundary past which nothing can return, can be gentle, weak enough that you might cross it without feeling anything unusual at all. This creates a strange kind of neighborhood in the universe. Small black holes are violent neighbors. Their gravity changes so sharply over short distances that anything nearby gets torn apart long before it reaches the horizon. Large black holes, especially the supermassive ones found at the centers of galaxies, are calmer neighbors, at least at their edges. The stretching still happens eventually, deeper inside, but at the horizon itself, space can feel almost ordinary, smooth, unremarkable, giving no obvious sign that anything unusual is happening. This is one of the strange truths sitting inside this whole mystery. The horizon is not a wall. It is not a line you would see or feel. Around a giant black hole, you could drift across it while looking at your own hands, thinking everything was fine, unaware that leaving had already become impossible. Some physicists wonder whether this gentle crossing is the honest picture, a place where nothing special happens locally, where physics stays smooth and continuous. Others propose a competing idea called the firewall hypothesis, which suggests that something at the horizon might destroy you instantly and violently the moment you arrive, no matter how large the black hole is. Under this view, quantum effects near the horizon could create a kind of energetic wall, meeting you with a burst of destruction rather than a quiet slide inward. These two pictures, the gentle one and the firewall one, do not agree. Both come from careful, well-supported mathematics. Both cannot be fully correct. Which one describes reality remains an open question, unresolved by any experiment we can currently perform. What can be said is this: somewhere between the outer neighborhood of a black hole and its center, tidal forces grow without limit. Whatever gentle or violent thing happens at the horizon, the stretching eventually becomes total. Your body, your thoughts, the space between your atoms, all of it would be drawn into a single thinning line, aimed at a point we still do not fully understand. The neighbors of a black hole, then, are shaped by this uneven pull. A star drifting too close gets stretched and shredded, its gas pulled into a bright spiraling disk before disappearing across the horizon. A person falling in follows a smaller version of the same fate. The forces are the same forces that shape ocean tides, only turned up to a strength our planet never has to feel. You would not notice the moment gravity turned dangerous. There is no lying in space that glows or hums to warn you. There is only the slow growing difference between how hard gravity pulls on one part of you and how hard it pulls on another, until that difference becomes the only story left to tell. Let's think about your shadow, not the dark shape that follows you on a sunny day, but something stranger, a shadow made of light itself, cast against the glow of everything falling into a black hole around you. Picture a black hole surrounded by a thin, bright ring of gas. That gas glows white hot as it spirals inward, and it lights up the space around the black hole like a lamp behind smoke. Against that glow, the black hole itself blocks the light. It leaves a dark circle, a kind of silhouette. Astronomers have actually captured images of this. The dark circle they photographed is not the event horizon itself, but something slightly larger, called the shadow. It is one of the strangest photographs ever taken, because it is a picture of an absence. Here is where the extremes begin. The shadow of a black hole is bigger than the black hole itself, sometimes more than twice the size of the event horizon, the invisible edge past which nothing returns. This happens because light bends. Photons that pass close to the black hole get pulled into curved paths by gravity, looping partway around before escaping or falling in. Some of that bent light reaches your eye or your telescope from angles that make the dark region look larger than the true boundary hiding inside it. You are not just seeing a black hole, you are seeing space itself, warped into a lens. Now think about your own shadow. If you could somehow stand near one of these objects and still survive, which you could not, but imagine it anyway, light from behind you would bend around the black hole in long, looping arcs. In theory, you might see faint, repeated images of your own body stretched thin and curved into rings, echoes of light that circled the black hole more than once before reaching your eyes. Some physicists call these photon rings. Each ring would be a fainter, more distorted copy of the last. It is one of the few places in the universe where light can lap itself again and again, tracing the same tight orbit, before finally escaping or disappearing across the horizon for good. This is where the records stack up. The largest known black hole shadows belong to supermassive black holes at the centers of galaxies, objects with masses billions of times greater than our Sun, so large that their shadows can be measured across enormous cosmic distances. The smallest black holes, by contrast, may be tinier than a single atom, remnants some scientists think could have formed in the extreme heat just after the birth of the universe. No one has confirmed these tiny black holes exist. Their possible existence remains an open question, one more mystery layered onto an already mysterious object. Temperature offers another extreme and a strange reversal of what you might expect. Massive black holes. The giants are colder than almost anything in the universe, colder than the coldest lab on Earth, colder than the space between stars. Tiny black holes, if they exist, would be the opposite, blisteringly hot, radiating energy quickly and possibly evaporating away entirely over time, through a slow leak of particles called Hawking radiation. Bigger, in the world of black holes, means colder and calmer. Smaller means hotter and more restless. It runs against most intuition about heat and size. Spin adds one more layer of extremity. Some black holes rotate at speeds close to the theoretical limit allowed by physics, dragging space and time around themselves in a swirl called frame dragging. Near a fast-spinning black hole, you would not be able to stay still, even if you tried, because space itself would carry you sideways, whether you wanted to move or not. Your shadow, your reflection, any light tied to your presence, would be swept along in that same rotation, smeared into a spiral rather than a simple curve. None of these extremes answer the deeper question this episode sits with. Seeing a shadow, measuring a spin, calculating a temperature, none of it tells us what happens to the information that falls across the horizon. The shadow only shows us the outer boundary of the mystery, drawn in light. What lies past that boundary? What becomes of you the moment you cross it? Stays hidden inside the dark circle. Every image only outlines. The extremes give us numbers. They do not give us answers. Let's slow down here and look at something small, something almost too quiet to notice, tucked inside the larger mystery of falling. It is this: every atom in your body carries information, not in the way a book carries words, but in a deeper sense. The exact position of every particle, the exact spin, the exact way your cells are arranged, all of it is a kind of pattern. Physicists call this information. It is the full, detailed record of you, written into the arrangement of matter itself. Ordinary physics makes a quiet promise about this pattern. It says, information can change shape, but it cannot vanish. Burn a letter, and the words seem to disappear. But the smoke, the ash, the heat drifting into the air, all of it still holds the pattern, scrambled but technically present. In principle, a being who could track every atom of smoke could reconstruct the letter. Nothing is truly erased. This idea has a name. Scientists call it unitarity, the rule that the universe keeps its records, even when we cannot read them anymore. A black hole seems to break that promise. Here is the small, strange detail. When something falls past the horizon, the boundary past which nothing returns, It seems to leave the observable universe entirely. The information about your shape, your memories, the pattern that made you specifically you, appears to fall somewhere no instrument can follow. And if the black hole eventually evaporates, slowly leaking energy away as what is called Hawking radiation, that radiation appears smooth and featureless. It does not seem to carry any trace of what fell in. If the pattern is truly gone, physics has a problem, a real one, not a philosophical shrug. It would mean the universe forgot something it promised never to forget. This is called the black hole information paradox. It sits at the center of modern physics, like a small stone in a shoe, uncomfortable, impossible to ignore. One idea, favored by many theorists, is that the information is not lost at all. It is only hidden very well as you cross the horizon. Some researchers propose that a smeared, scrambled copy of your pattern gets painted onto the horizon itself, like a shadow pressed flat against a surface. The horizon becomes a thin skin, holding an encoded record of everything that ever fell through it. In this view, nothing is destroyed. It is only rewritten into a form we do not yet know how to read. A competing idea takes the paradox more seriously. It suggests the information really might be lost, and that this means our understanding of gravity or of quantum mechanics needs a deeper correction we have not found yet. In this view, the paradox is not a puzzle to be solved with clever bookkeeping. It is a signpost, pointing toward some missing piece of physics, something as significant as gravity itself once was to Newton. The detail worth sitting with, the beautiful and unsettling part, is that both of these can be argued mathematically. Neither camp is guessing wildly. Both are following the equations as far as they go, and the equations run out before they reach an agreement. If you fell into a black hole, this quiet argument would be happening about you specifically, not about black holes as a category, but about the actual pattern of your actual body, the private architecture of your particular life. Somewhere in a physicist's notebook, the question of whether you persist, encoded, or truly end is still an open line of research. There is a smaller detail inside this large one. Some theorists have studied how fast information could leak back out, if it leaks out at all, through the slow trickle of Hawking radiation. They found that the radiation must, at some point, start changing its pattern if information survives. This shift has a delicate name, drawn from a curve on a graph that looks like the edge of a musical instrument. Researchers call it the Page curve, after the physicist who first described it. Recent theoretical work, using tools borrowed from the mathematics of holograms, suggests the curve might behave in a way that supports the idea of hidden information, but this remains calculation, not confirmation. No one has watched a real black hole evaporate. No one may, for a very long time. So the small detail becomes a large one again, a single unresolved question folded into every atom that has ever crossed a horizon. Whether the universe is a careful librarian, keeping every record in some unreadable script, or whether it sometimes, quietly, lets a book burn all the way down. For now, both possibilities remain open on the page, waiting for evidence that has not yet arrived. For a long time, physicists were content to let black holes keep their secrets. The equations that described them came from Einstein's theory of gravity, and for decades that theory seemed to answer every question anyone thought to ask. A black hole was simple. It had a mass, a spin, and almost nothing else. Anything that fell in, the thinking went, simply became part of that mass. The details of what you were made of, the pattern in your bones, the memories in your mind, all of that would blur into the black hole itself, like a drop of ink dissolving into a dark pool. Then, in the early 1970s, a young physicist named Jacob Bekenstein asked a quiet question that would not let go of him. He wondered whether a black hole might have something like temperature, something like heat. At the time, this idea sounded almost absurd. A black hole, after all, does not glow. It swallows light. It seemed to be the coldest, most final object the universe could produce. But Bekenstein noticed something in the mathematics. The size of a black hole's horizon, the boundary past which nothing returns, always seemed to grow whenever anything fell inside. It never shrank. That pattern reminded him of another law, one from ordinary physics here on Earth, about heat and disorder always increasing over time. If a black hole followed a similar law, Bekenstein reasoned, then maybe its horizon carried something like a record of everything that had ever crossed it. Maybe the surface of a black hole was not empty. Maybe it held information, spread thin across every inch of that dark sphere. This was one of the first moments anyone suggested that a black hole might remember, in its own strange way, what it had consumed. Young Stephen Hawking took this idea seriously enough to try to prove it wrong. He worked through the mathematics, expecting to find a flaw. Instead, in 1974, he found something that startled him and the entire field of physics. Black holes were not perfectly silent after all. They radiated. Very faintly, very slowly, a black hole would leak a soft glow of particles out into space, a process the world now calls Hawking radiation. Over immense stretches of time, this radiation would carry away the black hole's mass, until eventually the black hole would shrink and vanish entirely. This discovery answered one question and opened a far stranger one. If a black hole eventually evaporates completely, what happens to everything it once swallowed? Hawking's own calculations suggested the radiation leaving the black hole would be random, with no trace of what had fallen in long ago. No memory of a star, no memory of a person, just featureless heat spreading outward into the cold dark. If that were true, then information, the very pattern that made anything itself, could be genuinely destroyed, not scattered, not hidden, erased from the universe entirely. This troubled many physicists deeply, because one of the deepest rules in physics says information cannot be destroyed. Not really. It can be scrambled beyond recognition, but it should still exist somewhere, in principle recoverable. Hawking's calculations seemed to break that rule. For decades, this became known as the black hole information paradox, and it split serious physicists into two camps that still exist today. One camp trusts the smooth, continuous world described by gravity, where falling into a black hole feels uneventful, at least at first. The other trusts the strange, granular world of quantum mechanics, where information is treated as sacred and unbreakable. Both frameworks have been tested and confirmed again and again in their own domains. Near a black hole, they seem to disagree. You can imagine standing between two trusted maps of the same coastline, each drawn by careful hands, each correct in every detail checked so far, yet disagreeing about what happens at one particular shoreline neither map maker could ever visit. That is where physics stands today. Hawking himself continued working on this question for the rest of his life, revising his own views more than once. Other physicists proposed that information might leak out, subtly encoded within the radiation itself, hidden in patterns too fine for early calculations to catch. This idea remains one of the leading possibilities, though it is not yet settled. No one has watched a real black hole evaporate, No one has measured Hawking radiation directly, not yet. Everything rests on mathematics, careful reasoning, and educated disagreement among people who have spent entire careers staring into the same equations. What began as a quiet question about heat became one of the deepest open problems in modern physics, one that touches directly on whether everything you are could, in some form, survive. Most people picture a black hole as something cold and final, a hole in space that only takes. But black holes may also give something back, very slowly, in the form of a faint glow. Physicist Stephen Hawking proposed this in the 1970s, and it remains one of the strangest ideas in modern physics. He suggested that black holes are not perfectly black at all. They may leak a thin stream of particles into space, a whisper of radiation that now carries his name. Here is the strange part. This radiation does not come from anything falling out. Nothing can climb back over the horizon, the invisible edge past which nothing returns. Instead, the glow seems to come from empty space itself, right at the boundary of the black hole. Empty space, it turns out, is never quite empty. Tiny pairs of particles are thought to appear and vanish everywhere, constantly blinking in and out of existence for the briefest possible moment near a black hole's edge. Something unusual can happen to this quiet flickering. One particle of a pair might fall inward, while its partner escapes outward into space. Hawking calculated that this process would let the black hole radiate energy outward, bit by bit, forever losing a little of itself with each escaping particle over immense stretches of time. This slow leak means the black hole is shrinking. It is, in a very real sense, evaporating. The scale of this is almost impossible to picture at rest. For a black hole with the mass of our Sun, the glow would be so faint and the evaporation so slow that it would take far longer than the current age of the universe to lose any noticeable amount of itself. Smaller black holes, if they exist, would evaporate faster, glowing brighter as they shrink, ending perhaps in a final burst of radiation. If you stood near a black hole at the very end of its long life, you would feel the last of its gravity fade, not with a sudden vanishing, but with a quiet, gradual thinning into nothing at all. This is where the surprise deepens into a puzzle. The radiation escaping the black hole appears to carry no information about what fell in. It looks, as far as anyone can measure, completely random. It does not seem to remember whether the black hole formed from a collapsing star, a cloud of gas, or in principle from you. If that is true, then everything that ever fell in, every arrangement of atoms, every detail of a body or a mind, would be erased when the black hole finally finishes evaporating. Not hidden, not stored somewhere unreachable, simply gone, with nothing left behind to reconstruct it. That idea troubles physics at its foundation. One of the deepest rules in physics says that information should never truly disappear. The universe is thought to be reversible in principle, meaning that if you knew everything about a later moment, you could, in theory, work backward to know everything about an earlier one. A black hole that erases information without a trace would break this rule entirely. Physicists sometimes call this the information paradox, and it remains unsolved. Some researchers wonder whether the radiation only looks random because our calculations are incomplete, and that with a better understanding of gravity, tiny correlations would appear, secretly encoding what fell in after all. Others wonder whether information is preserved in ways we cannot yet detect, perhaps recorded on the horizon itself, or released at the very last instant of evaporation in some hidden final flash. Both ideas are theories, not settled answers, and they do not fully agree with each other. What makes this idea so strange to sit with is the quiet mismatch between two things that both seem true. A black hole appears to slowly disappear, glowing faintly as it goes, following gravity's gentle math. And yet, the deepest laws we know insist that nothing about you, not one detail, should ever be lost completely. Both cannot be fully right at the same time, and no one has found the piece that reconciles them. So the black hole shrinks, glowing so faintly that no telescope built so far could ever hope to see it. Somewhere in that glow, physicists suspect, is the answer to whether the universe forgets. For now, the light simply drifts outward into the dark, carrying its secret, if it carries one at all, farther from any place we can read it. A physicist named Stephen Hawking spent much of his life thinking about this quiet loss of warmth we just described. He wondered what it meant that a black hole could slowly leak its heat away as faint radiation and vanish, while carrying no record of what it once swallowed. This single idea connects to almost everything else in this mystery, the way one thread in a woven blanket touches every other thread around it. Think about how the sun warms the ocean, and how that warmth stirs currents that circle the whole planet. One process reaches into another and another, until the whole system moves together. A black hole works inside a system too, though a much stranger one. It sits inside the fabric of space and time, and whatever it does to that fabric echoes outward into the deep laws that describe everything else in the universe. Hawking's insight was that black holes are not simply endless traps. They glow, faintly, losing mass over unimaginable spans of time, through what we now call Hawking radiation. This radiation appears to carry heat, but not history. It tells us nothing about the shapes, textures, or memories of what fell in long before. If that is true, then something troubling follows. The universe seems to erase information quietly, forever, and physics has a rule that says it should not be able to do that. This rule is called unitarity, a word that simply means information is never truly destroyed, only ever rearranged. If you burn a letter, the words become smoke and ash, but in principle, someone with perfect tools could trace every atom back to the page it came from. Black holes seem to break this promise entirely. They take in your shape, your history, every arrangement of atoms that made you who you were, and they return only plain, featureless heat. Nothing about you seems to come back out. This is called the information paradox, and it remains one of the most stubborn, open questions in physics. One camp holds that information truly is lost, and that black holes are a rare place where the old rules simply do not apply. Another camp insists the universe cannot break its own promise, and that the information must be hiding somewhere we have not learned to read yet, encoded in the radiation itself, or written invisibly on the horizon's surface. If you imagine standing at the edge of a black hole as it slowly evaporates over billions of years, you might picture your own information smeared very thinly across the radiation, drifting outward. Not gone, some researchers argue, just spread so thin and so subtly patterned that no instrument we have could ever gather it back together. It would be like your voice scattered into every echo in a vast canyon, technically still there, but never assembled into words again. Other researchers wonder if that comforting picture is simply wrong. Perhaps the black hole truly is a boundary where old rules stop working and something new takes their place. Something we do not yet have the mathematics to describe. Both groups agree on the equations that describe gravity outside the black hole, and both agree on the equations that describe particles and radiation. They simply cannot agree on what happens where the two must meet. This unresolved tension connects far beyond black holes themselves. It touches quantum mechanics, the rules that govern the smallest particles, and general relativity, the rules that govern gravity and the shape of space. These two frameworks work beautifully in their own separate worlds, the way ocean currents work beautifully without needing to explain volcanoes. But black holes force them to sit in the same room, and so far they have not learned to speak the same language there. If you fell into a black hole, this disagreement would not feel like anything falling on you. There would be no tremor, no sudden alarm. Your body would simply continue on its path, unaware that two branches of physics were quietly arguing over your fate. Hawking himself changed his position more than once during his life, a sign of how open this question truly remains, even among the people who study it most closely. He is remembered for pointing at black holes not as simple traps, but as places where the universe seems to whisper a question it has not yet answered. Some nights, looking up, it is worth remembering that the universe keeps large mysteries in plain sight, glowing faintly, waiting patiently for us to catch up. Let's think about how our idea of a black hole has changed, slowly, over the years, like a photograph coming into focus in a dark room. When the first mathematics of black holes appeared, over 100 years ago, most physicists treated them as strange curiosities, a solution to an equation, not a real place. The idea that something so total could exist felt more like a trick of numbers than a fact about the sky. For decades, the black hole lived mostly on paper, a shape in someone's notebook. Slowly, the picture changed. Astronomers began to find objects in space that behaved exactly as the equations predicted. Stars orbiting something invisible, light bending around a patch of nothing. The black hole moved from theory to observation, and with that move, the questions became sharper. It was one thing to wonder about a mathematical object. It was another to wonder what would happen to a real body, falling toward a real edge, out there in the actual dark. Then came a second shift, quieter than the first. Physicists started asking not just what a black hole does to matter, but what it does to information, the deep pattern of arrangement that makes you, you. This was a new kind of question. It didn't ask about crushing or stretching. It asked about erasure. Could the universe simply lose the details of something that once existed? For a long time, the answer seemed obviously yes. A black hole swallows, and swallowed things do not come back. That answer stopped satisfying people once Hawking radiation entered the picture. If a black hole slowly leaks energy and eventually fades away, and if that leaking energy carries no trace of what fell in, then the information seems to vanish for good. But a foundational rule of physics insists that information cannot simply disappear. It can scramble, it can hide, it can become nearly impossible to read. It is not supposed to be destroyed. This is the mirror at the center of the mystery. Two trusted ideas facing each other, each reflecting a version of reality the other one denies. One side of the mirror shows a black hole that truly erases. The details of your body, spread out across billions of atoms, would be gone the way a word disappears when you erase it from wet sand and let the tide come in. The other side of the mirror shows a black hole that preserves everything somehow in a form we cannot yet decode. Some researchers picture the horizon like a page, holding a compressed record of everything that ever crossed it, written in a script we have not learned to read. If you fell in, This version says a version of your pattern would remain, smeared thin across the surface, waiting. Neither picture has won. The mathematics for each is sound within its own frame, and that is part of what makes this so quietly unsettling. It is not a case of one side using better tools. It is two careful descriptions of the universe, built by careful minds, arriving at endings that cannot both be true. For you, this means the fate of your own atoms, in this one specific and unlikely situation, is still undecided by the field that is supposed to decide such things. The change continues even now. New tools, especially ideas borrowed from the physics of information itself, have started to bend the mirror slightly. Some recent theoretical work suggests that the radiation leaving a black hole might carry more structure than we once thought, hidden in correlations we are only beginning to notice. This does not settle the argument. It shifts it. The conversation that began with simple curiosity about strange equations has grown into one of the most careful, most contested conversations in physics. It helps to remember that black holes themselves are also changing slowly, all the time. They grow as they feed. They shrink, almost imperceptibly, as they radiate. Even the ones far above your head tonight are not fixed objects. They are processes, unfolding across timescales longer than any human life, longer than our species, long enough that the universe itself might grow old before some of them finish evaporating. So, the mirror keeps turning. One face shows a universe that forgets. The other shows a universe that never truly can. We do not yet know which face is the true one, or whether both are somehow partial reflections of something stranger still. For now, it remains an open question, resting quietly at the heart of modern physics, patient, unresolved, and still very much alive. Light near a black hole does something strange. It bends, it stretches, it slows down, at least from where you stand watching there. And in that bending light, some physicists think they see a clue about what happens to everything that falls in, including you. Picture yourself drifting towards the horizon, the invisible edge past which nothing returns. From far away, a friend watches your body grow dimmer and redder as you approach. This is not because you are fading. It is because your light has to climb out of a deepening well of gravity, and climbing costs it energy. Each photon you send arrives weaker, stretched toward the red end of the spectrum, the way a siren drops in pitch as it passes and pulls away. Your friend never actually sees you cross the edge. Your image just gets dimmer and redder, slower and slower, until it seems to freeze, then fade past the point of detection. In this outside view, you are smeared thin across the horizon like a photograph left too long in the sun, forever almost arriving. But you, falling, would not feel frozen at all. You would cross the horizon smoothly, still whole, still glowing with your own ordinary light, noticing nothing unusual in that instant. This is one of the strangest parts of the mystery. Two honest observers, one falling, one watching, would describe two different endings for the same body. Neither is lying. Both are reading the light correctly. The disagreement is built into the geometry itself, and no one has found a way to make both stories fully agree. Some researchers wonder if this mismatch is a clue about where your information goes. The holographic principle, an idea still very much under debate, suggests that everything about you, every detail needed to describe your body, might be recorded as a shimmer of light and shadow on the horizon itself. A thin, glowing skin wrapped around the darkness. In this view, the horizon behaves like a screen, and you become a pattern of light etched onto it, encoded the way a hologram encodes a three-dimensional scene onto a flat piece of film. If this is right, nothing is lost. It is only rewritten in a form we do not yet know how to read. Other physicists are not convinced the light tells that story at all. They point out that if your information truly gets smeared across the horizon should not behave like calm, empty space where you fall through easily. It might instead behave like a wall of fire, a firewall, where the light and energy waiting for you are so intense that you would be destroyed the instant you touched the edge, long before gravity ever had the chance to stretch you thin. In this telling, there is no gentle passage. There is only an ending, bright and immediate, hidden from outside eyes by the very darkness that gives the black hole its name. Both descriptions use the same light. Both use the same equations of gravity and quantum theory. And yet, they lead to opposite scenes. One where you drift through untouched, one where you meet a wall of radiance the moment you arrive. This is not a simple disagreement over facts. It is a sign that our two best theories of the universe, general relativity and quantum mechanics, do not yet fit together cleanly at the horizon. The light is honest. Our understanding of it is not yet finished. If you fell toward a black hole and looked back at the universe you are leaving, you would see something beautiful and unsettling. The stars behind you would smear into rings of light, bent by gravity into circles and arcs. A sky folding in on itself like liquid glass. The light of everything you ever knew would still be reaching you, distorted but present, for a little while longer. You would still be you, watching your own history curve around the darkness ahead. No one has resolved which version of your ending is correct. The slow encoding onto a horizon, the sudden brightness of a firewall, or something else entirely that neither idea has imagined yet. The light gives us data. It does not give us certainty. Some theorists suspect the true answer requires a version of physics we have not fully written down, one where gravity and quantum information finally speak the same language. Until then, the glow at the edge of a black hole remains, one of the most patient riddles in the sky, still shining, still unread, still waiting for someone to learn how to see what it is really saying. Space has no air. Sound needs air or water or some kind of matter to travel through. So a black hole makes no sound at all, not in the way your ears would understand it. And yet, if we take the vibrations of the universe and translate them into tones we can hear, something strange happens. We find a kind of music hiding in the silence. Two black holes spiraling together send ripples through space itself, and scientists have turned those ripples into sound. The result is a soft chirp, rising in pitch, then gone. It sounds almost like a single drop of water landing in a still, dark pond. That chirp carries a puzzle inside it. When two black holes merge, they seem to lose some of their surface area in the collision. For decades, physicists believed a black hole's horizon could only grow, never shrink. This was called the area theorem, and it seemed as solid as any law in physics. But new mathematical work suggests something more delicate is happening at the edges of these mergers, something that touches directly on the mystery we have been sitting with tonight. If information about everything that ever fell into a black hole is written on its horizon, then any change to that horizon is a change to the story of everything it holds. This brings us back to the paradox at the center of this episode. One idea says, the horizon copies your information the instant you arrive, spreading it thin across the surface, like a name written in sand at the edge of the tide. Another idea says nothing is copied at all. Instead, everything about you falls inward, unchanged, until it reaches a place where our equations simply stop making sense. Both ideas cannot be true in the way physicists currently understand the universe. If information is smeared across the horizon and also carried whole into the depths, then somewhere, secretly, you would exist twice. Most physicists agree this cannot happen. The rule against it even has a gentle name: black hole complementarity. It suggests that both descriptions are true, but only if no single observer can ever check both at once. A friend watching you fall would see you spread thin on the horizon. You yourself would feel nothing unusual at all, sliding through without a mark. The two of you would never be able to compare notes. The universe, in this view, protects itself from contradiction by making the two stories permanently unshareable. Not everyone finds this comforting. Some physicists argue that a closer look at the mathematics reveals a problem hiding underneath the calm surface of complementarity. If the horizon truly holds a copy of your information, then something in the fabric of space, right at the edge, should behave violently, not gently. This is the seed of the firewall idea we touched on earlier, and it remains unresolved. If you crossed a horizon like this, the calm freefall we described earlier might not exist at all. Instead, the very last moment of your body's story might end in a sudden release of energy at the boundary. Not deep inside, but right at the edge everyone once thought was so unremarkable. No one has measured this directly. No instrument has looked at a real event horizon closely enough to say which version of the story is correct. What we do have are these gravitational wave chirps, quiet signals pulled from the vibration of space itself, hinting at how horizons behave when they merge and change. Some researchers hope that listening closely enough to enough of these mergers might one day reveal whether horizons truly hold information the way the holographic idea suggests, or whether that idea will need to bend into something new. There is a strange comfort in translating something so vast into something as small and human as a sound. The chirp of two black holes merging lasts less than a second. It rises, and then it fades into silence again, the same silence that filled the space before it. If you were floating far outside a black hole, near enough to feel its pull, but far enough to survive, this is the closest thing to a voice it would ever offer you. Not a word, not a warning, just a brief note in the dark, carrying a question we still cannot fully answer about whether anything, including you, could ever truly be erased. For now, the sound fades, the paradox stays open, and the universe keeps its own quiet counsel on which version of the story, if either, is the true one. Space near a black hole does not behave the way space behaves anywhere else. The equations that describe it come from Einstein's theory of general relativity, and they say something quiet and strange. Close to the center, space itself begins to move. Not the things inside space. Space itself. Picture a river flowing toward a waterfall. Far upstream, the water moves slowly. Closer to the edge, it speeds up. Right at the edge, it moves faster than anything in it could swim against. The event horizon, the boundary where nothing can escape, is the place where the flow of space reaches the speed of light. Past that point, no signal, no light, no motion in any direction can carry you back upstream. This picture comes from a solution to Einstein's equations found by a physicist named Carl Schwarzschild in 1916, just months after Einstein published his theory. Schwarzschild worked out the math while serving in the German army during the First World War. He sent his solution to Einstein by letter. It described, with strange and simple elegance, exactly how space and time would bend around a single point of concentrated mass. He died the following year. He never saw how far his equations would reach. The numbers in that solution are almost embarrassingly simple. The radius of the event horizon depends on only one thing: the mass of the black hole. Double the mass, and you double the radius. For something with the mass of our Sun, that radius is about 3 kilometers. For something with the mass of the Earth, it would be about the size of a marble. If you compressed your own body down to its Schwarzschild radius, it would be smaller than the width of an atom's nucleus. The formula fits on a single line. The strangeness it describes does not. Inside that radius, the mathematics does something even stranger. The roles of space and time seem to trade places. Outside the horizon, you can choose to move forward, backward, sideways through space, but time always moves one direction. Inside the horizon, the equations suggest that falling toward the center becomes as unavoidable as the forward march of time itself. You could no more stop yourself from approaching the center than you could stop yourself from aging one more second. Some physicists describe this as time and space swapping their usual jobs. Whether that description reflects something physically real or simply reflects the limits of the equations we are using remains an open question. The ratios do not stop there. Compare the black hole's mass to its surface area, and you find another elegant relationship, one that led physicist Jacob Bekenstein and later Stephen Hawking to a startling idea. A black hole's entropy, its measure of hidden information, is proportional not to its volume, but to the area of its horizon. This single ratio helped inspire the holographic principle, the idea that everything about a three-dimensional space might be fully described by information written on its two-dimensional edge. If that principle holds, the numbers describing your body as you cross the horizon might be rewritten, compressed, and spread across that surface like a pattern etched in glass. Whether that pattern still counts as you is a question the mathematics cannot answer alone. Not every theorist agrees on how far this elegance should be trusted. General relativity gives smooth, continuous answers, curves without seams. Quantum mechanics, which governs the smallest scales of nature, insists that information comes in discrete steps and must always be preserved somewhere. The two frameworks agree beautifully everywhere in the universe we can test, and yet they seem to give incompatible answers about what happens at a black hole's center. One theory says space becomes infinitely curved at a single point. The other suggests that infinite is a sign the math has simply run out of room to describe what is really there. If you could hover just outside the horizon and watch the equations play out, you would see numbers behave the way tides behave, smooth, patterned, almost musical, right up until they are not. The elegance is real. The Schwarzschild radius, the entropy ratio, the way mass alone decides so much. All of it works with a precision that still surprises physicists who have spent decades with it. But elegance is not the same as completeness. Somewhere past the horizon, the simple math runs into a wall it was never built to cross, and no one yet knows what waits for it on the other side. At the very center of a black hole, the mathematics points to something strange. It points to a singularity, a place where density becomes infinite and space stops making sense. Picture all the mass of a collapsed star, squeezed into a point with no size at all. The equations of general relativity, the theory that describes gravity as curved space, simply break down there. This is not a comfortable answer. It is the place where physics runs out of things to say. Some researchers see the singularity as real, a true edge to space and time itself. Others see it as a sign that general relativity has reached the limit of where it can be trusted. Think of a map that works beautifully for an entire country, then suddenly shows nothing but blank paper at one small town. The blankness does not mean the town does not exist. It means the map was never built to show it. Many physicists suspect the singularity as like that blank spot, a place where a deeper theory, one that includes both gravity and quantum mechanics, would show something else entirely. Quantum mechanics is the physics of the very small, the rules that govern atoms and particles. It does not get along well with general relativity, the physics of the very large. Each theory works with remarkable precision in its own domain. Near a singularity, both domains matter at once, and the two theories give answers that cannot both be true. One idea, called loop quantum gravity, suggests that space itself is made of tiny discrete pieces, like grains of sand too small to ever see. If that is right, space might refuse to shrink past a certain size. The collapse could stop, or even bounce, rather than crushing down to nothing. Under this view, there may be no true singularity at all, only a very tight knot at the center that our current tools cannot resolve. Another idea comes from string theory, which proposes that particles are tiny vibrating strings rather than points. In some versions of string theory, the singularity gets smoothed into something finite, a small but not infinite structure. The details differ from loop quantum gravity, but the goal is the same. Both approaches try to replace the sharp, impossible point with something gentler, something that mathematics can actually describe. Here is where the balance feels fragile. If the singularity is truly infinite, then whatever falls in, including every atom that once made up you, may be crushed into a state with no size and no structure at all. There would be nothing left to unfold, nothing left to read. If the singularity is instead a stand-in for something smoother, then perhaps the information about you is not destroyed. It might be held in a tightly wound form we simply cannot yet describe. If you could somehow survive the fall, unharmed, and look toward the center, you would not see a point. You would see the enormous, gentle curve of horizon around you, silent and dark, giving no hint of what waits ahead. Your instruments would fail long before you reached whatever lies at the middle. No signal you sent could tell the outside universe what you found. This is part of why the singularity sits at the heart of the larger puzzle about information. If everything that falls in is truly destroyed at a point of infinite density, then the information describing it seems gone for good. That would break a rule many physicists hold dear, the rule that information can change form but never fully disappear. If the singularity is softened by quantum effects instead, there may be a way for that information to persist, tucked into structure we do not yet have the mathematics to see. The fragile balance is this, too. Of our best theories, each tested and trusted in its own realm, cannot agree on what happens in this one small extreme place. Change the assumptions slightly, and the outcome flips between total erasure and quiet preservation. It is a bit like a bridge built from two different sets of blueprints, each perfect on its own side, meeting in the middle at an angle that does not quite line up. No experiment has looked inside a real singularity. No signal can escape to tell us which picture is closer to true. For now, the center of a black hole remains a boundary of knowledge as much as a boundary of space. A place where the universe seems to ask a question it has not yet answered for us. Somewhere out in the dark, two black holes are circling each other. They have been circling for a very long time, drawing closer with every pass. Each one holds its own history of everything it has swallowed. And when they finally touch, something happens that puts our whole question about lost information to its hardest test yet. Picture two of these silent giants, each with a mass many times that of the sun, spinning around a shared center like a pair of dancers who cannot stop. As they spiral inward, they stretch and squeeze the space around them. Space itself starts to ripple, the way a pond ripples when two stones sink into it at once. These ripples are called gravitational waves, and they carry outward at the speed of light, long after the two black holes have merged into one. Here is where the mystery deepens. Before the merger, each black hole may have had its own horizon, holding its own tangle of encoded information, if the horizon truly holds such a thing at all. When the two collide, their horizons do not simply add together, like two pools of water joining into a bigger pool. For a brief and violent moment, the combined shape twists and rings, vibrating like a struck bell, before settling into the smooth, calm sphere of a single new black hole. Physicists call this final settling phase the ring down. During that ringing, the horizon's geometry is far from simple. What happens in that chaos to the information each black hole was carrying? Some researchers wonder if it simply merges, the way two conversations blend into one when two crowds meet in a hallway. Others wonder if something is lost in the noise, shaken loose during the violence of the collision, never to be recovered. If you could stand at a safe distance and watch this happen, you would not see fireworks or a flash of light. Black holes do not glow, and this event makes almost no light at all. You would feel it instead, as a passing tremor in space, a warping so slight that on Earth, the first ones we detected stretched every kilometer of matter by less than the width of a proton. Your body would pass through that ripple and never notice. It would stretch you and squeeze you by an amount smaller than anything your senses could register, and then it would move on, carrying its message toward some other corner of the universe. That message is really the point. The gravitational waves themselves may be our clearest hint yet about what black holes are truly made of, mathematically speaking. Some theorists have proposed that the pattern of the ring down, the specific frequencies at which the newly formed black hole vibrates before it goes still, could reveal tiny departures from the smooth predictions of general relativity, the theory that first described these objects. If black holes carry structure at their horizon, structure related to stored information, perhaps that structure would show up as faint irregularities in the ringing. So far, the signals we have caught still match the simplest predictions closely. But the instruments are young, and the search is far from finished. There is a competing view worth sitting with as well. Many physicists expect that a merged black hole, once it settles, looks exactly like any other black hole of the same mass and spin, with no trace left of the two histories that combined to form it. This idea is sometimes called the no-hair expectation. The notion that a black hole reveals almost nothing about its past once it is done merging. If that is right, then whatever information problem exists, it exists quietly, hidden below any signal we know how to measure. The merger would look clean and simple from the outside, even if something troubling is happening to information underneath. Either way, watching two black holes merge is watching two of the universe's most complete erasures joining into one. Whatever happened to the structure of everything each one had consumed, that structure is now interwoven, if it exists at all, inside a single, larger unknown. We cannot yet read the ripples closely enough to say what survives and what does not. The waves keep crossing the universe, faint and patient, carrying a message we are only beginning to learn how to decode. For now, the ringing settles into silence, and the mystery settles with it, waiting for better ears to listen. Picture two black holes far off in the dark, slowly circling each other. They have been doing this for a long time, drawing closer with every pass, bending the space between them into something like a spinning drain of night. Eventually they touch, they merge, and for a fraction of a second, the fabric of space itself rings like a struck bell. That ringing is real. We have detected it. Detectors on Earth, built to sense motions smaller than the width of a proton, have picked up the faint tremor of these mergers happening millions or billions of light years away. The signal is called a gravitational wave, a ripple in space and time itself, spreading outward at the speed of light, carrying no light of its own, only motion. It passes through you constantly, right now, in this room, in a wave too small to feel. Your body stretches and compresses by an amount smaller than an atom's width, and you never notice. Some researchers wonder if these ripples might one day answer the deepest part of our mystery, the question of whether anything about what falls into a black hole is ever truly gone. A merger between two black holes should, in principle, carry some trace of what each one contained. The wave might carry a whisper of the information locked inside. If scientists could read that whisper closely enough, they might learn whether the horizon keeps a record, or whether it burns every record clean. Right now, our instruments cannot read that deeply. The gravitational waves we catch tell us the mass of the black holes, their spin, how fast they merged. They do not yet tell us anything about the information paradox, the puzzle of whether the details of what fell in were destroyed or hidden somewhere we cannot yet reach. But the ripples keep coming. Every merger anywhere in the universe sends its wave outward in every direction, forever, growing fainter, but never fully stopping. In some sense, the echo of every collision is still out there, spreading through the dark long after the event itself is finished. Think about what that means across time. 1 billion years from now, our sun will have swollen into a red giant, and Earth, as we know it, may no longer exist in any familiar form. Galaxies will have drifted farther apart, some merging, some torn loose from their clusters, following slow gravitational currents we can only partly trace. Stars will burn out by the trillions. Matter will cool, and new stars will still be born from gas and dust that has waited patiently for the right conditions. Whatever technology exists then, if anything like us still exists to build it, may be able to catch those ancient ripples with a clarity we cannot imagine. This is one possibility worth sitting with. The information a black hole seems to erase might not be lost so much as smeared very thin, spread across a horizon, and then radiated back into the universe over spans of time longer than stars live. If that is true, no single ripple carries the full answer. The pattern would build slowly, wave after wave, collecting somewhere in the folds of space-time, like sediment settling at the bottom of a very deep, very patient ocean. It would take almost unimaginable time and precision to ever read it clearly. A competing view holds that no amount of future listening will resolve this, because the paradox may be built into the mathematics itself, a genuine contradiction between how gravity behaves and how information behaves at the smallest scales. Some physicists think the answer will come not from listening harder, but from finding an entirely new framework, one that unites gravity and quantum mechanics in a way we do not yet have. Until then, every gravitational wave we detect is a message with the return address blacked out. If you imagine yourself drifting in the space between galaxies, waiting through the slow unwinding of stars and time, you would feel nothing pass through you but the faintest of tremors, over and over, forever. Each one a black hole finishing something. Each one might be carrying, somewhere inside its shape, a fragment of an answer we have not yet learned to hear. The universe does not seem to be in a hurry to tell us. It keeps ringing quietly, patiently, waiting for something, someday, capable of listening closely enough. Most of the black holes we have talked about tonight are enormous. They weigh as much as suns, or as much as millions of suns pressed into a single point. But there is another kind, one that exists only in theory, so small it would fit inside a single atom. Physicists call these primordial black holes. The idea is that they may have formed in the first fraction of a second after the universe began, when matter was so dense that tiny pockets of it could have collapsed on their own without needing a dying star at all. No one has ever confirmed that a primordial black hole exists. They remain a hypothesis, a shape drawn on a chalkboard, a gap in our knowledge with a name attached to it. But if they are real, they would behave differently from their giant cousins in one important way. Stephen Hawking's own calculations suggested that the smaller a black hole is, the faster it radiates its mass, away as Hawking radiation. That faint outward glow we talked about earlier. A black hole, the mass of a mountain, might have finished evaporating billions of years ago, ending its life in a final burst of energy, rather than a slow fade. This detail matters for our mystery because it compresses the whole question into a shorter frame. If a small black hole can form and fully evaporate within the age of the universe, then whatever information it swallowed has already reached its ending, whatever that ending turns out to be. We are not just wondering about some far future event. We may be wondering about something that has already happened, quietly, somewhere in the dark, countless times. Some researchers have wondered whether primordial black holes could make up some portion of dark matter, the unseen mass that seems to hold galaxies together without giving off any light of its own. It is a tidy idea. Dark matter is invisible, and a black hole is invisible too, at least in the sense that it emits no light of its own before it evaporates. Like most searches for tiny primordial black holes have come up empty, and many physicists think dark matter is something else entirely, some kind of particle we have not yet detected. The two mysteries sit near each other without touching. That is its own kind of quiet fact. Here is where the rules might bend. Everything we have described tonight, the horizon, the singularity, the radiation, the paradox of erased information, comes from combining two of our best theories of physics: general relativity, which describes gravity and curved space, and quantum mechanics, which describes the small, twitchy behavior of particles. These two theories work beautifully on their own. They simply refuse to agree with each other at the center of a black hole. Some physicists think a future theory, perhaps one that unifies gravity with the quantum world, will show that black holes never truly reach a singularity at all. Instead, matter might reach some extremely dense but finite state, then bounce, or transform, or pass into something we do not yet have a name for. If that is true, then the question we have circled all night, whether the arrangement that made you you is destroyed or hidden or preserved, might have an answer we simply do not have the mathematics to write yet. It would not mean the mystery was solved tonight. it would mean the mystery was waiting for tools we have not built. If you think about your own body for a moment, resting quietly right now, you are made of atoms forged inside stars that lived and ended long before the sun existed. Those atoms have already survived one kind of ending. The calcium in your bones was once inside a star that could no longer hold itself up. In a strange way, you are already made of leftover information from a cosmic event you cannot remember and never witnessed. Whether a black hole could do something similar, taking you apart and turning you into a different kind of remainder, is a question physics has not closed. The honest answer tonight, as it was in every section before this one, is that we do not know. We have Hawking's radiation, the holographic principle, the firewall idea, string theory's soft and blurry horizons, all reaching for the same target from different directions, none quite touching it yet. Small black holes, if they exist, only remind us that the clock on this question may be shorter and stranger than we assumed. The universe keeps its answer close, for now, in the dark, near the edge, just out of reach. We have come a long way tonight, out past the orbit of every planet you know, out to the dark edges where gravity grows so strong that even light gives up and stays. We have watched a body stretch and a horizon glow with borrowed heat, and two whole theories of physics stand at odds over one simple, aching question. What happens to everything you are if you fell all the way in? And we still do not know. Maybe the information about you gets smeared across the horizon, written into some flickering, invisible skin around the dark. Maybe it rides out slowly, folded into the faint warmth of Hawking radiation, scrambled so completely that no one could ever read it again. But not truly gone. Maybe there is a wall of fire waiting at the edge, ending the story before it even begins to fall. Or maybe our equations are simply missing something, some deeper idea we have not found yet, that will one day make all of this feel obvious. Each of these ideas is held by careful, serious minds. None of them has won. This is the strange comfort of a real mystery. It does not need to be solved tonight for you to rest inside it. The universe has kept this secret for billions of years, curled up quietly at the center of galaxies, in the dark hearts of dead stars, patient in a way nothing alive could ever be. It will keep the secret a while longer. You do not have to carry it. You only have to notice it is there, the way you might notice a lighthouse blinking far off across black water, and then let your eyes fall closed anyway. Picture, instead, something gentler, a blue and white planet, turning slowly in the dark, wrapped in thin clouds that drift like breath on cold glass. Somewhere on its curve, night is falling right now, sliding westward the way it always has, patient and unhurried. Lights come on in small windows. Oceans settle into long, slow swells under a quiet moon. Nothing there is falling toward any edge. Nothing there needs to be. It is simply turning, the way it has turned for more mornings and more nights than anyone has ever counted. If you were floating far above it, looking down, you would see how small all our questions look from that height. The black holes, the horizons, the arguments about information and fire and shadow, all of it would shrink to a single thought, held gently in a much larger dark. Your body, resting in bed right now, is doing something a black hole can never do. It is breathing. It is warm. It is still for tonight, entirely and simply yours. There is a kind of peace in not knowing everything. The universe is not finished revealing itself, and maybe it never will be, not fully, not to us. Somewhere, radio dishes still listen for the last whispers of colliding black holes. Somewhere, someone is still working out the math of the horizon, still hoping the two great theories might finally agree. That work will go on without you tonight, quietly, the way starlight keeps arriving long after the star itself has changed. You can let it go on without you. You can rest. Let the picture soften now. The planet keeps turning. The galaxy above it keeps its slow, silent wheel. Arms of pale light drifting outward into a dark that has no edge we have ever found. Somewhere far past all of it, a black hole waits, holding its question the way it has always held it, patient, dark, unhurried. It does not need an answer from you. It never did. You are here, warm and small and entirely whole, held by a universe far larger than any question it has yet to answer. Whatever is true about horizons and information and the edges of things, it can wait for morning, and it can wait for many mornings after that. For now, let your breathing slow. Let the dark outside your window be simply dark, familiar, and kind. We may understand this mystery someday. We may not. Either way, the stars will still turn, the planet will still spin, and you will still be here to wonder about it again tomorrow night. Rest now. The universe is patient, and so, for tonight, are you. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.